Welcome to This Explainer. Okay, so today we're diving into what I can only describe as a real-life mathematical detective story. It all starts with this genuinely fascinating puzzle dropped onto the Prime Puzzles forum by Davide Rotondo back in January 2023. It's known as Conjecture 95. Now, I know math can sometimes feel like a finished book where all the rules have already been written, but every so often someone spots a hidden pattern in the numbers that completely defies expectation. Rotondo did exactly that with something called the 2-1 Pascal triangle. It looked like pure magic, and he challenged the world to prove whether it was a profound mathematical truth or just a coincidental illusion. Here's our roadmap for this explainer. First, the Pascal triangle. Then the first conjecture, followed by the second conjecture. After that, we'll see how the community responds, and finally, proving the math.
All right, part 1, the 2-1 Pascal triangle.
Before we get into the heavy polynomial algebra that ultimately cracked this case, we really need to visualize the game board our math detectives were playing on. I mean, what makes this specific triangle so special, right? Most of us know the standard Pascal's triangle, the one where the outside edges are all ones. But the 2-1 Pascal triangle, it operates a bit differently. As you can see, starting on the second row, we introduce a 2 on the left side. It seems minor, but this one little tweak fundamentally rewrites the triangle's underlying DNA. It creates these unique numerical ripples as you go down the rows. The numbers combine and grow in a totally distinct way, generating coefficients that might look completely standard at a glance, but are actually hiding some incredibly wild secrets.
Moving on to section 2, the first conjecture.
So here's where it gets really interesting. Rotondo made this mind-bending observation about prime numbers hidden right inside these rows. He noticed something that literally no one else had caught. He realized that if you look at a row and check to see if the second coefficient from the right is a prime number, this hidden rule just kind of unlocks. If it is prime, he proposed this hyper-specific correction process. Watch this. You take the third coefficient from the right and you add +1. Then you take the fourth and add -2. The fifth gets +3. Basically, you're overlaying alternating natural numbers, +1 -2 +3 -4, right onto the row. And when you do that, something absolutely incredible happens. Let's actually test this on the fifth row so you can see how it builds. Based on the triangle's underlying polynomial coefficients, Rotondo applied his alternating adjustments. You take that 9, add 1, divide by 5, and boom, you get a clean 2. Take the 7, subtract 2, divide by 5, you get 1. Take the 2, add 3, divide by 5, you get 1 again. So after applying those +1, -2, and +3 corrections, every single resulting number is cleanly divisible by 5. No messy decimals, no fractions remaining. It is absolutely perfect. And the crucial point here, the whole so what of this, is that 5 isn't just some random number. It's a prime number. According to Rotondo's first conjecture, this prime number status is the exact key that triggers the mathematical magic trick. Seriously, if that second coefficient from the right wasn't prime, this gorgeous, elegant divisibility just wouldn't work. The primes are literally the key unlocking the entire structure of the row. Okay, section 3, the second conjecture. But hey, Rotondo didn't stop there. He actually had another observation up his sleeve. And this time, he shifted the focus away from the horizontal rows and looked at the diagonal lines cutting through the triangle. He hypothesized that if the second coefficient from the right in a given row is prime, well then the corresponding numbers in that diagonal, excluding the one at the very edge, must all be multiples of that exact same prime. Let's look at the 7th row because it demonstrates this perfectly. That second coefficient from the right is 7. If we trace its diagonal, we pull out the numbers 7, 14, and 7. And exactly as the conjecture predicts, every single one of those numbers is perfectly divisible by the prime number 7. It's such a gorgeous visual pattern. But, in mathematics, a pattern isn't a fact until you can mathematically prove it'll happen every single time, out to infinity. Which brings us to the real cliffhanger of our explainer. On January 14th, 2023, Rotondo basically threw down the gauntlet with a single, daunting challenge to the math community on the Prime Puzzles forum. He just said, prove that the two conjectures are true or false. Is this an absolute, unbreakable law of the 2-1 Pascal triangle, or does the pattern eventually just fall apart? That brings us to section 4, the community responds. Math is rarely a solitary pursuit these days. Between January 21st and 27th, 2023, so literally just a week after the puzzle went live, a team of independent mathematical detectives stepped up to crack the case. We're talking about Mauro Fiorentini, Jan van Delden, Emmanuel van Tiegem, and Georgios Kalogeropoulos. They completely crowdsourced the investigation. And what's absolutely fascinating to me is that they didn't just collaborate. They tackled the problem from completely different angles. Every single one of them brought their own distinct mathematical tools to the table to prove, once and for all, that Rotondo's patterns weren't just a lucky fluke. And finally, Section 5, Proving the Math. To really appreciate how they pulled this off, we need to briefly look at the heavy mathematical machinery they used. Let's unpack the logic of how you translate a visual triangle into an ironclad proof. So Mauro Fiorentini came out swinging with something called Dixon polynomials of the first kind. Now don't worry, you absolutely do not need a PhD in algebra to grasp what he did here. Basically, Mauro figured out a way to translate the visual structure of the triangle into a strict algebraic formula. By using these Dixon polynomials, he was able to precisely define any specific term in any row as an absolute value, which set up an equation that could be rigorously tested against the rules of prime numbers. To spring the trap, Mauro combined his polynomial equations with Wilson's theorem. If you're not familiar, Wilson's theorem is this classic rule of modular arithmetic. It states that if n is a prime number, then n minus 2 factorial is congruent to 1 modulo n. I know that sounds like a mouthful, but it's really just a fancy way of saying it leaves a very specific remainder. By injecting Wilson's theorem right into his Dixon polynomial formula, Mauro essentially forced the divisibility rule. He mathematically proved that if n is prime, the modified terms simply must be divisible by n. There's literally no escaping it. Now, what's super cool here is the collaboration itself. In math, knowing something is true is great, but proving it in multiple ways, that builds a foundation of concrete truth. While Mauro was over there using advanced Dixon polynomials, Emmanuel von Tighem and Georgos Kalogeropoulos went a totally different route. They actually proved the exact same phenomena using binomial coefficients and classical modular arithmetic. Let's take a look at how Georgos built his case. Georgos logically broke the whole triangle down into a few specific steps. First off, he expressed the entire triangle as a function of n and k. Next, he mathematically inserted Rotondo's alternating +1 - 2 adjustments directly into the formula. And finally, he applied Lucas's theorem. By walking through these exact steps, Georgos proved that for any prime n, those adjusted binomials will always invariably cancel out to 0 modulo n. Or, in plain English, they will always be perfectly divisible by that prime number, every single time. Meanwhile, Emmanuel, working on his own track, arrived at a really precise formulation. If you look closely at the tail end of his equation, you'll see a sequence involving powers of -1. Well, that mathematical sequence perfectly mirrors the alternating +1 - 2 + 3 correction process we physically looked at earlier. Emmanuel proved that the visual trick Rotondo spotted, it's not a trick at all. It's actually a deeply embedded law of how binomial expansions behave the moment you introduce prime numbers. And of course, Emmanuel didn't just stop at the first conjecture. He went ahead and easily dismantled the second one regarding the diagonals. He mathematically isolated those diagonal elements and proved that if the expression 2n - k equals an odd prime, which represents those specific diagonal jumps, the resulting term absolutely must be divisible by that prime. Just like that, it was an open and shut case. Ultimately, the combined efforts of these incredible mathematicians across just 1 week in January 2023 resulted in this highly satisfying mic drop moment for Mauro Fiorentini. He simply stated, both conjectures are true. Together, they permanently solve Rotondo's puzzle, turning a curious visual observation into a proven, undeniable law of mathematics. As we wrap up this explainer, I really want to leave you with this thought. The Pascal triangle, in all its various forms, has been studied for literal centuries. Yet, a fresh set of eyes looking at the 2,1 variation found a completely undiscovered pattern of primes just hiding right there in plain sight. It's a great reminder that the universe, even the rigid, seemingly solved universe of mathematics, is still full of magical patterns just waiting for the right detective to come along and find them. So what else are we looking at every day without truly seeing? Thanks for joining me on this mathematical deep dive. And remember to keep your eyes open for the patterns all around you.